We are going to describe here the Thomas-Fermi model, which can be considered the first kind of density functional theory, because this model includes the electronic density as a key ingredient to solve the problem. It was derived in 1927 by Thomas and Fermi independently, and the main challenge they have was to characterize the electronic charge density in the atoms. Of course, this is a very challenging problem nowadays as well, because we have many electrons that are strongly interacting each other. And they thought that instead of looking for the electronic wave functions, it could be more efficient to look for directly to the electronic charge density. So they proposed a model for that. It's a semi-classical approximation in the sense that they are combining quantum calculations with classical approximations for the electrons that are immersed in external potential. And we are going to call that external potential Vx. So first we are going to start with an expression for the total energy of the system in terms of the electronic charge density. So this is the expression we have for the total energy of the system, and it includes three terms, and we are going to analyze these three different terms. So the first term, it's describing the kinetic energy of the electrons. In order to have that expression is based on the uniform electron gas approximation. So if you remember, in the uniform electron gas approximation, where of course the electronic charge density is considered to be constant, and here of course as we have an external potential, the electrons are not free anymore, and we cannot consider that the electronic charge density is going to be constant. But in this uniform electron gas approximation, the expression we have for the total energy per electron was the following. It was 3 over 10, 3 pi squared to 3 n to 3. Okay, that was the expression we have for the total energy per electron. And we want to derive the total energy of the system, not per electron, the total energy of the system. So we are going to do the following. We are going to multiply that expression with the total number of electrons we have per unit volume. And the total number of electrons we have per unit volume is n. So we are going to multiply that expression with n. So if we do that, we multiply with n, we have n to 2 to 3 times n is n to 5/3. So that's the expression we have. And this is therefore the energy we have per unit volume. So we have now to integrate over the whole volume in order to have the total energy of the system. And this is the expression that we have here. But of course here, n in the uniform electron approximation, the electronic charge density was constant. And here is not constant. Here it depends on position vector. But we are going to consider that the variations on the electronic charge density are smooth enough so that the approximation, the expression we have for the uniform electron gas approximation can be also applied here. Of course, this is just an approximation. So again, the first term here is the kinetic energy of the electrons. Of course, this is a quantum calculation in the sense that in order to derive that expression in the uniform electron gas approximation, we consider that the electrons are plane waves and they obey the Pauli exclusion principle so that each state can just be doubly occupied because of the two spin states and so on and so forth. It's a quantum calculation. And then we have the two additional terms, they correspond to the electrostatic potential. So the first one is giving the interelectronic electrostatic potential. So if we consider that the electronic charge density is given by nr, then the electrostatic potential associated with that charge distribution is just given by that expression. This is just a classical approximation for the electrostatic potential. And besides that, as the electrons are immersed in this external potential, then we have an additional term to the electrostatic potential associated with the external potential, which is also uh, um, a classical expression for that. Okay, now we have an expression for the total energy of the system as a function of the electronic density. And now, of course, this electronic density and R, it's variable, and we don't know which is the expression for that electronic density when the electrons are immersed in that external potential. So how can we get an expression for that once we have the general expression, even though within this approximation we have considered before, for the total energy of the system? So we know how to do that. We know that the total energy, or the energy that the system is going to take, is the one that minimizes the total energy of the system. So we have to search for the electronic density that minimizes the total energy, but this electronic density is subject to a constraint. The integration on the whole volume of the electronic density is equal to n, which is the number of electrons. And the number of electrons we are going to consider to be a fixed number. And so we know how to minimize the some function with some constraints. We have to apply the Lagrange multipliers method. And for that, we are going to build a new functional, which basically is the energy we have defined before, minus mu, which is the Lagrange multiplier, and the constraint that the electronic density has to satisfy. So once we have built the new functional, we are going to look for the minimum with respect to the density, and for that we are going to look for the functional derivative of f with respect to electronic density, making it equal to 0. So if we make the functional derivative of f with respect to n and make it 0, that's the expression we have. This is the equation that the electronic density has to satisfy. So we have found an equation for the electronic density. This equation is called the Thomas-Fermi equations for the electronic density, and it has an integral form in the sense that the electronic density is inside an integral. And it makes this equation quite complicated to solve. By the way, here, the Lagrange multiplier appearing here has a physical meaning. And it's quite easy and quite straightforward to derive which is the classical meaning of that Lagrange multiplier here. And for that, considering that the functional f has two terms, the energy and this term here, making the functional derivative of f with respect to n has to be 0, and as f has two terms, it is to see that the functional derivative of f with respect to n, we can write it in this way: the functional derivative of e with respect to n minus the functional derivative minus mu, and the functional derivative of n of this term is just equal to 1. So this has to be 0. So basically from here we have that mu, which is the Lagrange multiplier, is equal to the functional derivative of the total energy with respect to the density. And this is the chemical potential. So mu has the meaning of the chemical potential. And mu is just a number, it has a value. So, and the value, of course, it's going to depend on the system we have. Basically, it's going to depend on the external potential we have. So for each system, we have to we can specify which is going to be the chemical potential of the system. So we have that equation here, which is the integral version of the Thomas-Fermi equations in terms of the electronic density. And we're going to derive another version of the Thomas-Fermi equation, which is going to be in a differential form. And for that, we are going to do the following. This term here is basically the induced potential associated to that electronic density. Okay, and we are going to call it V. So V is going to be the induced potential associated to the electronic density N. Okay, so in the following, okay, we're going to derive the differential equation version for these Thomas-Fermi equations. And for that, how I want to see first that this V, as we said before, it's the induced potential associated with that electronic density. And these two magnitudes here, the electronic density and the induced potential, they are both related through this Poisson equation. So the Laplacian of V is just equal to 4 pi times n, the electronic density. Okay. Considering the equations before, the Thomas-Fermi equations we derived before, here these equations, here we can easily isolate n from here. We can bring just these two terms to the other side of the equation and just isolate m from here. And if we do that, and considering we call this term, we are going to call it v, so we can easily see that just isolating n from the Thomas-Fermi equations before, we have that n is equal to this term here. Okay. Now, this n here, considering the Poisson equation, we can write instead of n, we can write the Laplacian of v over 4 pi. And bringing 4 pi to the other side, we have this equation here, the Laplacian of v of the induced potential. The induced potential we have here is these coefficients here, where this k is the prefactor appearing in the kinetic energy term in the within the uniform electron gas approximation. So here, which multiplies this mu, which is the Lagrange multiplier, which basically is the chemical potential, the external potential that we have to specify, which is in order to solve that equation, plus the induced potential. So this equation that was derived from the integral equation of the Thomas-Fermi equation that we derived before is just a differential equation that induced potential is satisfying, because here the unknown is the V, the induced potential. So we have a differential equation for V, not for the electronic density, but for the induced potential. That, of course, we need to specify which is the external potential in order to solve that equation. But this is the equation that we have to solve. It's more easily, it can be solved more easily than the integral equations that the induced potential satisfy. So once we have that equation, we are solving that equation for induced potential, then we can go to the Poisson equation and have a solution for the induced electronic density. And once we have the electronic density, then we could go back to the expression we have for the total energy of the system, and we can get the total energy of the system we are analyzing, which are electrons, which are immersed in this external potential. So basically, we already have the equations that we need to solve. And now the next step we are going to do is we are going to solve that equation for some specific problem. And specify the problem means specify the external potential.